Welcome back to Analog Circuits. In this class, I'm going to cover mainly review material. You've already seen this before. We'll go through a few fundamental building blocks when we are designing circuits. We'll review some of the key theorems. And based on that, we will build the rest of the lectures. It's important that all of you review these theorems and be conversant with them, because I'm going to refer to them over and over in the following lectures. So let's get started. So first we will go through a few circuits basics. In this, we will begin with introduction to different elements, circuits elements we are going to play with in this class. So let's start with, I'm sure all of you know these elements, you've used it. This is called a voltage source, DC voltage source. This is a current source, again a DC current source. Then you're familiar with this element, resistor, then the two parallel plates, capacitor and inductor L. There is also one element you will see, it's a dependent source called dependent source, and it's generally shown in the following way. So there is a controlling something that controls. Let me redraw this again. There is a controlling parameter, and this is the final output. And generally we denote them as star C, star S, star being either voltage or control, voltage or current. So for example, you could have a voltage controlled voltage source or a current controlled voltage source, or similarly current controlled voltage source or current controlled current source. So these are four different combinations, and when you go to circuit simulation, you will be using these dependent sources quite a lot to model various things which are happening in the circuits. Okay. Apart from these, we will be using devices. Let's start with the really fundamental. This is diode. Okay. Now, just so that you remember how to read this particular device, if you look at this device from here, you will see a K, and hence you can say that this is a cathode, which is a negative terminal. Okay. And if you look at it from here, you will it will look like an A triangle. Okay. So we call that anode or positive terminal, and when you apply positive voltage to the anode, then the current will flow in this direction of the arrow, which is indicated by this this triangle. Okay. And if you try to apply positive potential on this side, okay, then it won't conduct, the diode will not conduct. So it acts like a valve, one-way traffic. Okay. Then we will also review transistors. The first one we will go through are called bipolar junction transistor, okay, or called BJT. And here is the symbol for, so this is called NPN transistor. Okay. We are going to review them in detail along with what's really going on inside the device to understand how does it work as an amplifier, the current, the carrier transport and things like that. Okay, but we won't get into the device physics aspect of it. That you will be exposed to in a different class in lot more detail. Now here is NPN transistor. This arrow terminal always is the emitter terminal. Okay, and this is your collector and this is your base. So this NPN transistor has a brother and it's called PNP transistor. Okay, the arrow is here. Again, since the arrow is over here, this is called emitter, this is collector, and this is your base. Okay, so this is your PNP transistor. The next transistor, the most popular transistor that you will get to play with is called metal oxide semiconductor transistor, or called MOSFET transistors. And the symbol for the transistor, MOSFET transistor, is as follows. This one is called NMOS transistor or NMOSFET, and wherever you have an arrow, that particular terminal is called source. The opposite terminal is called drain terminal, and this is the control electrode, which is called gate. Okay, again, NMOS transistor has a brother or a sister, which we draw like this. We call this PMOS transistor. Okay, the arrow terminal is called source, and the opposite terminal is a drain, and this is your gate. Okay, so now we know these are the elements that we will be using in this particular class. Later on, if you get into circuit simulations, then these are the basic elements that you will use to put together various circuits. Okay. Now we will go through some of the basic circuits laws. First one, I'm sure you are familiar with it, Kirchhoff's law. Now, and they are, there is Kirchhoff's current law and Kirchhoff's voltage law. So let's go through KCL. When I want to explain KCL, I would like to show you a picture such that, let's say there are a bunch of pipes, okay, and they are all connected together like this, something like this, and then there is another one here, and there is another one. Okay, so now there is, let's say we started pushing water from these two pipes. Okay, so now if the water is flowing at a certain rate from these two pipes, then that water has to come out from these sides, and there is no water that can stay inside this particular node as such, right? Because the water has to flow out somewhere. So this is a good way to understand. In circuits, instead of these pipes, we have wires which are like conduits, and instead of water, we have charges. So let's say there is in circuits, when we draw the circuits, we often encounter a junction of various branches. So these are the branches, and this is a node where they come together. So Kirchhoff's current law basically says that if there is current flowing through all these branches, okay, and if you add all those currents together, and in mathematical terms we can say it's IK from k equal to 1 to n. If you add all these currents together, then the sum of them is 0. Important thing to remember here is the direction of the current. If you don't look at the direction correctly, then you may get a wrong answer. So in this particular law, we are assuming that all the currents have the same direction. Okay, so this is Kirchhoff's current law. We will be using this quite a lot. The next law we use quite a lot is Kirchhoff's voltage law, KVL. In KVL, we are looking at a loop inside a circuit. So there are a whole bunch of different branches inside circuit, and we identified a loop. So for example, there is, I'm just drawing the loop first, and then I'll put the elements in there so that it's clear. And let's say there is a voltage source here, there is another current source here, something like that, right? Now, and let's say there are these different elements, which are, there is a resistor here, there is an inductor here, there is another resistor, and things like that, and there is another element here, let's say. Okay, so these are different elements. Now, okay, we should have some other element here also. So these are all various elements. So what Kirchhoff's voltage law says that if you go around the loop, okay, and you add all the voltages together, then the sum total of all those voltages is 0. And again, in this case, you have to make sure the direction of the voltages that you are adding is all same. Okay, for example, like this. Now this one we have to fix. This should be plus minus, this should be plus minus, like this. So Kirchhoff's voltage law, you can write it in the format, again same way, K equal to 1 to N and Vk equal to 0. So if you add the voltages in a loop, then sum total of those voltages is 0, and that's Kirchhoff's voltage law. You're already familiar with it in your probably 11th and 12th, you're exposed to this. And this is what these two laws, we will be using them quite a lot. The next popular law that we use in circuits is Ohm's law. So in Ohm's law, let's say there is a resistor, and there is a voltage across the resistor VR, and there is a current flowing through the resistor, which is IR. So what, and value of the resistor is R. So Ohm's law says that VR is equal to R times IR. Okay, or the value of the resistance is equal to V divided by I across the resistor. Okay, now when we move forward in our as we get into more complex circuits, we talk about something called impedance. I'm just introducing the concept, and there we call it, the complex impedance is noted as Z, and in that case, again, the Ohm's law is valid, and it's written, this is, let's say, your impedance Z, and let's say if this is VZ, voltage Z, and let's say this is IZ, which is flowing here, then we say that VZ is equal to Z times I times Z. Okay, now one thing I want to mention is, why are we looking at these laws, right? And why are they so popular? So before these laws came into picture, you have to, every time you have to do the analysis, you have to write the differential equations for each component and things like that. Whereas using these Kirchhoff's current law, voltage law, or Ohm's law, what we are assuming, the basic thing we are assuming is that we can look at each component as an encapsulated component and not a distributed component. So it's like a lumped element, and we can apply these laws to them, and this makes our life a lot easier to do a quick hand analysis and understand the circuit, and that's the reason we use these laws all the time. Okay. Another theorem that we use in circuits is called Thevenin or Norton theorem. Okay, here again we are trying to simplify really complicated circuits so that we can, sometimes we can treat a complex circuits as a black box. because we don't care what's going on inside that box, and we would just like to look at two terminals and figure out what's really going on. So how do I model this particular circuit? So this is what this is where these two theorems or the same theorem comes into play. So for example, let's say you have I'm just putting everything in the box where you have a whole bunch of elements. You have a voltage source, you have a resistor, and a whole bunch of different configuration of resistors, capacitor, inductor, whatever you have in there. And then we are only looking at these two terminals. For example, you're doing something in the lab and you have a black box and there are only two terminals coming out and you want to figure out what's going on really inside. So then what you would do is you would apply Thevenin's theorem. So let's note that this is node A and this is node B. Okay, so what Thevenin theorem says that you can look at this and this is your R load. You can look inside this circuit. First of all, you would measure the voltage between node A and B in an open circuit fashion, which means that you would just take this box and simply measure this voltage first. Okay, look at using a voltmeter, and you will measure something called VTH, which is a open circuit voltage. Okay, and then what you will do is you will short all the independent voltage sources inside the box. Okay, so if there is any battery in there, you will short it out, and then you would find out what's the Thevenin resistance looking in the box. So you will measure RTH, and so key point here is you will short all independent sources, voltage sources, and then you will find equivalent RTH. That's what you'll measure. Okay, so in other words, what you will do is you take a black box. It has two terminals, and the first thing you will do is you will put a voltmeter and you will measure the voltage between A and B without any load, and that would be your open circuit voltage measurement, and let's say that comes out to be VTH. Then you will turn off all the, for example, if there is a battery inside, voltage source battery, then you will short that battery because you want that particular battery, according to this theorem, you would like to short that battery out, which means you will just connect the two terminals of the battery. You will remove the battery and you will short those two nodes of the battery wherever the battery was connected. And then once you are done with that, you will simply put an ohm meter or a multimeter between node A and B, and you will measure what is the R resistance measured between A and B, and that would be your Thevenin resistance between the two terminals. And then you can model these complex circuits as simple as this. Okay, you can say this is my equivalent A, point A and point B. Okay, and this would be RTH and this would be your VTH. Okay, so as far as you are considered, this is the way this black box, complex black box, I mean, this could have hundreds, thousands of elements, a network of elements and things like that, and then this is the way it's going to look like. And now we can connect our load resistance, which is our load, and then you can measure the actual what would you expect here, or what would we expect the current to be. So again, Thevenin's law helps you simplify a complex network and represent it with a simple voltage source and a resistance. The flip of the Thevenin's theorem is the Norton theorem, where we would pretty much do the opposite. So instead of voltage source, we would like to have a current source. So there what we would do is we would take this complex network, okay, and then there is this node A and B that we have, and we would short this, okay, and we would measure what is the current ITH flowing through that, okay, and that Once you measure that current, and then again the second thing that you would do is measure RTH, which I have already explained you how to do that, and then you can model this circuit as a Norton equivalent. Okay, so here the Norton equivalent would look like this. This is my current source, ITH, and then in this particular case you would put RTH like this, and that becomes your node A and node B. Okay, and then you can apply your R load and analyze what's going on inside this circuit. Okay, so these are real fundamentals that you should be conversant with. If you have not, if this is all new to you, then please refresh these basics.